So we're going to start talking about the ideal gas equation. So far we've seen that the volume is indirectly related to the pressure, or Boyle's law, that the volume is directly related to Charles' law, and that the volume of a gas is directly related to the number of moles, which is known as Avogadro's law. And I actually will get to that. Hopefully it makes sense that the more gas particles I have, the greater the number of moles, that the greater the volume needs to be at a temperature or a pressure of the system. If we combine these relationships, we can see that the volume is proportional to the number of moles times the temperature over the pressure. What we can do is use a constant to change that proportional symbol to an equals. And that proportionality constant is actually known as the gas constant. There are several values for it. The one that we will use most often is, or the one that I use most often, is this top one. Okay, and I have it memorized that the ideal gas constant, which is R, is equal to 0.8206 liters atmospheres over moles Kelvin. Memorize it. It makes your life a whole lot easier, particularly when you're taking a test. Okay. All right, so we've got that volume is proportional to those moles times temperature over pressure. Putting in the ideal gas constant, volume is equal to the gas constant times the number of moles times temperature divided by pressure. Moving pressure to the other side, we get a fairly famous equation that most people refer to as PVnRT. I kid you not. PVnRT. PV is equal to nRT. This is true for any gas that behaves ideally. Most often we make that approximation at room temperature and pressures. For most gases, it's a pretty good assumption. Okay, so how do we apply this? Well, we can look at some problems. We have calcium carbonate decomposing upon heating to give us calcium oxide as a solid and carbon dioxide as a gas. If I collect the carbon dioxide in a 250 milliliter flask, after the decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. And the question is, how many moles of CO2 gas were generated? Well, let's work this out. And this is a perfect problem to write out the given. Okay. I'm really asked for the number of moles of CO2 gas. So I know that the carbon dioxide is collected in a 250 milliliter flask, converting in my head to liters. The volume is equal to 0.250 liters. The gas has a pressure of 1.3. Pressure is equal to 1.3 atmospheres. Temperature is 31 degrees Celsius. In my head I went, wait, I can't use Celsius for gases. I need to convert that to Kelvin. So 31 plus 273 is 304 Kelvin. And my unknown is the number of moles, or N. So, working through the problem, I have P, I have V, I'm looking for N, R is a constant, I have T. Solving this equation for the unknown in terms of the other variables, I will have N is equal to PV over RT. So plugging in for P, 1.3 atmospheres, times the volume, 0.250 liters, R, hopefully 8206 liter atmosphere mole Kelvin, times temperature in Kelvin. Putting that in the calculator, 1.3 times 0.25 divided by 0.08206 divided by 304 gives me 0.13028 moles. Kelvins cancel, atmospheres cancel, liters canceled. I was left with 1 over moles, which ends up being moles. Significant figures, well, originally that was 2, but when I added to Kelvin it made it 3. This was actually 2 because it was initially just 250, and this was 2, so I am going to express my answer as 0.13 moles of CO2. Okay. We'll look at that in class. Let's see how we can manipulate the sides of the ideal gas law to come up with different values, okay, or different quantities. If we divide both sides of the ideal gas equation by V and by RT, we get N over V is equal to P divided by RT. Okay. Well, what do we know about N? Well, we know that the number of moles multiplied by the molecular mass gives me the mass. So if we multiply both sides of the equation by the molecular mass, I get mass over volume of the gas is equal to the pressure times the molecular mass over RT. What's mass over volume? That's the density. So the density of a gas is equal to m over v, which is equal to the pressure times the molecular mass over RT. So we only need to know the molecular mass, the pressure, the temperature, so we can calculate the density of a gas. That's actually kind of cool. So let's run through an example. So what's the density of carbon tetrachloride vapor at 714 torr and 125 degrees Celsius? Okay. I'm going to do given. I know that it's carbon tetrachloride. Oh, whoa. Sorry, I don't know where that came from. I can calculate the molar mass of that because it's 1 carbon, 12.01, plus 4 times 35.45. That gives me a molar mass of 153.81 grams per mole. Pressure is equal to 714 torr. I can't use it in torr because I've memorized R in terms of atmosphere, but I do remember that there's 760 torr in 1 atmosphere. So that gives me my pressure in atmospheres. 714 divided by 760, that gives me 0.9395 atmospheres. And my temperature is 125 degrees Celsius, but I'm dealing with gases, so I can't deal with Celsius. I have to make that into Kelvin. I did it wrong on my calculator. But it will be 398 Kelvin. So the density is equal to the mass over the volume, which is equal to the pressure times the molecular mass over RT, which is equal to the pressure, 0.9395 atmospheres, times the molar mass, 153.81 grams per mole, over R, 0.08206 liter atmospheres, moles, Kelvin, times 398 Kelvin, divided by. Putting that in my calculator, I get the density as 4.4245. Let's see, atmospheres canceled, Kelvin cancels, mole cancels, so I'm left as grams over liters. Looking at significant figures, I had 3, 3, 5, so I should report this as 4.42 grams per liter for that gas. Okay. What else can we do with it? Hey, we can solve for molecular mass. We can manipulate that density equation to enable us to find the molecular mass of a gas. So, if we're given the density of the gas, we can manipulate it to be molar mass is equal to the density times R times T divided by P. We'll look at a couple of questions in class that cover this. That's going to be all for the notes.